sports figures. Put your brain in the game.
If you want to hit a home run, that means you have to hit it over the outfield wall. That means I have to hit the ball far enough, right? No problem. See, hitting a home run isn't just about how far you hit the ball. It's also about what direction you hit it in. It has to be between the foul poles, right? See, for a lot of things, just one measurement isn't enough. For a home run, you need how far and which way. Running bases works the same way. To be a good base runner, you need speed. Speed is how fast something goes. Whew, that's speed. I just ran 360 feet in 3 seconds. That's 120 feet per second. That's 82 miles per hour. Pretty fast, right? But all that speed wouldn't do me any good if I went this way. Whew. See, speed is important to base running, but direction is just as important. Just like a home run has to go a certain distance, it also has to go in a certain direction. If I say I ran here at 82 miles per hour, or the ball traveled 400 feet, that's the amount or magnitude of the motion. In math, motion and speed are a scalar quantity. It just tells us the magnitude. But if I say I ran 82 miles per hour to first base, that's different, because it has both magnitude, how fast, and direction, which way. That's called velocity, and velocity is a vector quantity. So a scalar quantity isn't going to get me to second base. I need a vector quantity, speed and direction. Vectors, how much and which way? Vectors can tell us all sorts of cool stuff. All motion, whether it's a ball flying through the air or a bat swinging, can be broken down into its components. That's what we can do with vectors. We can break motion down into its components. That way we can figure out how it works, what makes it tick. To help us out with vectors, we've got Barry Larkin of the Cincinnati Reds. He's an 11-time National League All-Star and a 9-time Silver Slugger team member and a 3-time Golden Glove Award winner. Okay, Barry, velocity is a vector that tells us how fast something is going and which way. But there are other kinds of vectors.
Right, you can use vectors to show in which direction and how far objects move.
Oh, that vector is called displacement.
Correct. If I run from home to first base, you can use a displacement vector to show you how I got there.
Okay, how would we do that?
Well, from home to first base, the displacement would be 90 feet in the x direction and 0 feet in the y direction.
Those are coordinates on a Cartesian graph. In Cartesian graphing, we would use x and y axes to show the position of first base, right? Our units are going to be in feet. First base is going to be 90 on the x-axis, 0 on the y. That makes sense. First base is 90 feet from our origin, home plate. When we're working with vectors, we're talking about the relationship between 2 points. For example, the speed and direction something will move. We use the same Cartesian grid system, only we label the two-dimensional grid I, J. If we want to add our third dimension, we label that axis K instead of Z. Okay, so now we've got displacement that tells us how far and which way. What other kinds of vectors are there?
Well, like you were talking about before, velocity is a vector. It tells you how fast and in which way.
We could use velocity to describe a fly ball.
Right. You still have the IJK axis to show your direction, but now your unit of measurement would be speed.
If we created vectors for this home run ball, they would look like this. Our units of measurement are now in feet per second instead of feet. Our IJ axes still show direction. Now let's say the ball is traveling 15 feet per second down the I-axis and 80 feet per second up the J-axis. We would get a velocity of 15I plus 80J. How fast and which way? The ball's traveling in this direction, right? What velocity vectors do is allow us to split that direction into 2 components. They tell us how much of the ball's speed is traveling on the I-axis and how much is traveling on the J-axis. Okay, so what's missing from our home run vectors?
Well, the ball isn't moving flat on a two-dimensional grid like the runner would be. You've only got its I and J speeds.
Yeah, the ball's going up at the same time. That's a third direction.
That way, you can get its upward velocity, too.
Okay, let's try it. We need to add another dimension for our ball to travel in. The k-axis allows us to map the ball's velocity in the upward direction. The ball's upward speed is 72 feet per second, so we get the vector 15I plus 80J plus 72K. That vector accurately describes the velocity, the speed, and direction of our home run ball. Okay, so this is the velocity vector of our ball. What does it all mean?
Well, it breaks down the speed of the ball into different directions.
It gives us the magnitude, the speed, and the direction. How much and which way.
It's sort of weird though, right? I mean, we're used to saying something goes 90 miles per hour or something.
But that's just speed. This is velocity, speed, and direction. A vector.
So that's the velocity the ball got from the bat, and its direction is out over left field wall. But could something affect the ball's velocity while it's flying through the air?
If the wind is blowing, that could change its direction.
It could change its speed, too.
Right. But the cool thing about working with vectors is that we can figure out the effect of the wind on the ball and figure out if the home run is really a home run. Now, generally, wind only blows from side to side, not up and down. So let's go back to our two-dimensional vectors. Let's say the wind is coming directly out of the northeast at 15 miles per hour. That's 22 feet per second. We know that's going to slow the ball down and push it in this direction. But how much? To figure that out, we can make a vector of the wind. When we put the wind on our Cartesian grid, you see that it's exactly 45 degrees to our grid, exactly northeast, with a velocity of negative 16 feet per second I and negative 16 feet per second J. It's negative because both the I and J directions of the wind are against the direction of our grid, right? Here's the trick to graphing vectors. Now, you might think that if the ball is traveling in this direction and the wind is traveling in this direction, you put the arrows this way, head to head. But that's not right. You have to put the arrows this way, head to tail. You can even put the arrows this way, just so long as they're head to tail. So now we have the wind's vector, negative 16I plus negative 16J. Now what?
Well, the great thing about vectors is you can add them. You just add the I components and the J components of the vector.
Okay, that sounds pretty simple. All we do is add the vector components together to get the wind's effect on the ball. And we get negative 1I plus 64J, a new vector that shows how the ball will be traveling with the effect of the wind. When we add vectors together, the answer is called the resultant vector. Resultant vector. Get it? Whoa! And we always use a bolder arrow to indicate resultant. Our resultant vector shows us that with the wind, the ball's going to just barely go foul. In fact, thanks to vectors, we can quickly see that if the I component of the wind is greater than 15 feet per second, it will push the ball foul. Vectors make it all really easy. Real pilots use real vectors every day. An airplane is affected by the wind, so the pilot has to figure out the effect of the wind's velocity vectors. If you want to get where you're going, your pilot needs to use velocity vectors. Okay, guys, so what did we learn?
That scalar quantity gives us magnitude, like how far and how fast.
Vector quantities tell us how far, how fast, and which way.
We use vectors to map motion.
And all motion can be broken down into linear components using vectors.
Displacement, velocity, and force are all vector quantities.
Vectors can be added or subtracted to find a resultant force, like the wind's effect on the ball.
Everything you wanted to know about vectors. So you got this vector thing down now?
Yeah, I got it, but I'd rather play the game than try to figure it out.
Well, that's it. We'd like to thank Barry Larkin and our students, Colby, Ben, Jordan, and Larry. We'd also like to thank Disney's Wide World of Sports Complex, located at the Walt Disney World Resort in Orlando, Florida, for helping us out here today on ESPN Sports Figures Victory with Vectors. direction I'm going in.